Hello, my amazing students. This is Mrs. A, and I'm going to be doing 7.1, which is all about the population proportion, finding an estimate for the population proportion. And we're going to do that through creating a confidence interval. So I want you to think of 7.1 and 7.2 as basically being the same concept. We are creating a confidence interval, and if we are trying to find a 95% confidence interval, we want to be 95% sure that the true mean of the population is inside this interval. Okay, in order to create that interval, we're going to have to do a little bit of math. But once we finish the math, we're going to have an interval, and I want you to think of the interval kind of like a fishing net. If I wanted to be more sure that I was going to catch the fish, if I wanted to be 98% sure that I was going to catch the fish, then I would need a little bit bigger net. Okay, if I wanted to be only 90% sure, I might be able to shrink my net a little bit and still be 90% sure. So basically, the mean, it's not a great analogy, because when we're thinking about catching the population mean, the mean is not moving. The population mean is fixed. And so we are just trying to create a big enough net to make sure that we are reasonably sure we have the population, true population mean within that region. Okay, and then we can say we have a pretty good estimate of where it is. So listen carefully to each one of the slides, but I want you to get the big picture that all the way through 7.1 and 7.2, we're really doing the same thing. We're trying to create an interval called a confidence interval that's around the true mean, and we'll have the true mean inside it. Okay, that's the big picture of what we're trying to do in 7.1 and 7.2. So here it goes. Okay, so in just trying to give you a broad overview, in each of these sections, 7.1 and 7.2, we're going to discuss 3 different methods for doing a confidence interval. In each chapter, at the beginning of the key concepts, they're talking about a point estimate. Each section, not chapter, 7.1, 7.2, they're talking about a point estimate, a confidence interval, figuring out the sample size. That's what we're doing for the whole chapter, okay? Now, let's focus in on confidence interval here. This little sheet here is generally what we're going to be doing every time we figure a confidence interval. We're going to use different methods and different distributions, but the same type of pattern. So basically, we're going to identify our sample statistics, things like our sample size, our mean of the sample, our standard deviation of the sample. Maybe we have a true standard deviation of the population. We're going to identify those things. We're going to find the point estimate. In each and every case, we will find the point estimate. Either we're given the point estimate, because that would be our X bar or our P hat, or we have to find them out using the methods given. We need to verify that we can do it. Okay, so we're going to verify some requirements, and that varies with each method. In each one of these stay the same. We're going to find the critical value using the confidence level. We're going to find the margin of error, E. We're going to build the confidence interval, and then we're going to round the answer appropriately. That is the pattern of what we're doing here, and we're going to do it over and over and over again. Sometimes you're going to just find the critical value. Sometimes you're going to find the margin of error. Sometimes you're going to find the confidence interval, which involves those things. Sometimes you're going to find the point estimate. but this is a big picture of what's going on here. All right, so the first thing that we're doing is 7.1, and we're talking about estimating a population proportion. In 7.2, we're going to be talking about estimating a population mean. This involves finding a confidence interval. Okay, so here are your key concepts like I showed you on the piece of paper. Okay, we're going to be talking in each case about a point estimate, a confidence interval, and a sample size. Since the first section, 7.1, is about finding, estimating the p-hat, all right, so let's go back, estimate the population proportion. The p-hat is actually the sample proportion. We're trying to estimate the true population proportion. So we're trying to find the p, and we will be working with proportion in this one. Okay, so the sample proportion p-hat is the best point estimate for the population proportion p. So we're trying to find the p, but we can calculate the p-hat. And then the confidence interval is what we're going to build. It's going to be an interval, and we're going to talk more about that because that's the whole big picture of the whole section is confidence intervals. And then we're going to show different methods so that you can figure out what is the needed sample size in order to be able to estimate the population proportion given the level of confidence that we want to estimate it to. Okay, so the point estimate is a single value used to estimate a population parameter. Okay, in this case, we're going to be estimating the population proportion. Therefore, we're going to look for a p-hat. The sample proportion is the best point estimate for the population proportion. Okay, so the unbiased estimator, p-hat, is the point estimate because it is unbiased, and it is the most consistent of the estimators that could be used. An unbiased estimator is a statistic that targets the value of the corresponding population parameter. So in 7.2, we'll be looking for a population mean. In 7.1, we're looking for a population proportion. Okay, and in the sense that the sampling distribution of the statistic has a mean that is equal to or the corresponding population parameter. So remember what we talked about sampling distributions, and how the sampling distribution was when we did a distribution based on the sample means, and in this case, since we're doing the sample proportion, we did not really focus on the sampling distribution of the proportion because it's just not that big a deal in this class. So, but we are going to find the estimating the whole population proportion here. So, point estimate, and then the probability of success in a single trial of a binomial experiment is the true population proportion. We don't know that, but we're going to use the sample proportion as a point estimate for that. And then we're going to build an interval around that sample proportion in order to be confident to the level that we need to be that our true proportion is inside there. Okay, it's denoted by P as the population proportion, and p-hat is the sample proportion. Okay, now, so here we've got p-hat is the number of successes, which is x, in a binomial experiment. Remember, x was the number of successes, and then n is the whole sample size. So our p-hat can be calculated by number of successes over sample size. Okay, and then we call it p-hat.
And then we have this is talking about the p-hat, but it's also talking about, can we find a point estimate for Q, the population proportion of failures? Now, we obviously look for P more often than we look for Q, but we would find the point estimate for Q by just taking Q hat as 1 minus P hat, which we used when we did binomial distributions. And that's read as Q hat. So what is a sampling error? The sampling error is the difference between the point estimate, okay, so in this case the P hat, and the actual population parameter, in this case the P. So here they're talking for the mu, or the mean, is x bar minus mu, and for the P hat it's going to be P hat minus P. All right, so here we have an example. A Gallup poll was taken in which 1,487 adults were surveyed, and 43% of them said that they have a Facebook page. Based on that result, find the best point estimate of the proportion of all adults who have a Facebook page. So basically we took a sample, and the sample had a p-hat of 0.43, or 43%. So now we're trying to find out what is the true proportion of all adults that have, in fact, we'd be talking about adults who have a Facebook page. So basically 43% said they have a Facebook page. So we're talking about maybe all adults that have internet access. We'll say that, okay? Because the sample proportion is the best point estimate of the population proportion. We conclude that the best point estimate of P is 0.43. If using the sample results to estimate the percentage of all adults who have a Facebook page. Okay, now in this one they're not being very clear because there are a lot of countries that do not have even the internet abilities that would make a Facebook page possible. They're not being very clear on what they mean. Whether they're talking about all adults in the U.S., all adults all over the world. It's kind of nebulous, but for the purpose of what they're doing here, we're not going to get too nitty-gritty. Okay, in a survey of 1,000 U.S. adults, 662 said that it was acceptable to check personal email while at work. Find a point estimate for the population proportion of U.S. adults who say it is acceptable to check personal email while at work. Okay, so they're giving us 662 out of 1,000. So what is our point estimate? We don't know what the true population proportion of U.S. adults is, but we can get a point estimate, just like we did in the last example. 0.43 was the best point estimate we could come up with. So here we're going to have 662 over 1,000, which winds up being 0.662, or 66.2% is our p-hat, and our p-hat is our point estimate. It's the best we've got as far as knowing how many adults in the U.S. would say that it's okay to check personal email while at work. So now we get into the big deal. What is a confidence interval, and why do we care? A confidence interval is also an interval estimate, is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI, and the confidence level is very important. The confidence level is the probability 1 minus alpha. Now that little thing right there is an alpha, and such as 0.95 or 95% that the confidence interval actually does contain the true population parameter, assuming that the estimation process is repeated a large number of times. The confidence level is also called the degree of confidence, or the confidence coefficient. Okay, so we're going to look at some examples of this and figure out what this means. But before we do, here is a table of the most common confidence levels. and their corresponding alpha values. So we have corresponding alpha 0.10, and this is going to be 0.90 or 90%. Remember, the confidence level C is 1 minus alpha. And guess what? Alpha is 1 minus C. So they're complements of each other. 0.05, 95%. 0.01, 99%. As the alpha gets smaller, the confidence level goes up. Okay, so interpreting a confidence interval is very important. A lot of people will read it the wrong way or think that it means something it does not. We must be careful to interpret confidence intervals correctly. There is a correct interpretation and many different and creative incorrect interpretations of the confidence interval. So here, they've just made this one up. Okay, so here's a made-up confidence interval. Okay, we are correct if we say we are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. Okay, so basically they're saying the true P, the population proportion, is in this interval or range. And we're going to find that range. That's called a confidence interval. And it will be based on the level of confidence that we want to claim. Okay? If our confidence level goes up, you're going to see that this range gets wider. If our confidence level, if we don't need to be quite as confident, our interval goes down. Okay? So let's talk about some incorrect ways to interpret this. There is a 95% chance that the true value of P will fall between 0.405 and 0.455. There's not a 95% chance. Okay, P is P is P. It's already determined, and it's not being determined after, like, say, flipping a coin. Okay, the P already exists, and we're trying to develop an interval that has a level of confidence that the true P is in there. And the other one is also wrong. 95% of sample proportions will fall within 0.405 and 0.455. Okay, this is also incorrect. So we're talking about a confidence, a level of confidence, and remember what is correct. Okay, here's the correct one. We are 95% confident that the interval from 0.405 to 0.455 actually does contain the true value of the population proportion P. Okay, so let's stay away from the wrong ones and use the right one. So here is the process success rate. A confidence level of 95% tells us that the process we are using should, in the long run, result in confidence interval limits that contain the true population proportion 95% of the time. So the population proportion here, in this case, is 0.50. Okay, and so here, as we have these intervals, notice we're hitting that population proportion is in that region 95% of the time. Okay, so here we got a region, but we failed to get the true population proportion. So we should have, out of 100 times that we made this interval, we should have 5 of them that are failures and 95 of them that are that do actually have the population proportion in them.
Okay, so I have done a lot of YouTube searching throughout my teaching career, and the best explanation that I heard is thinking of the interval as a fishing net, but the fish is stationary. Okay, so if you wanted to be 99% 90% confident that you were going to catch the stationary fish. In other words, the fish is not swimming around. The true proportion is fixed. The true population mean is fixed. Whatever it is we're looking for, that is already fixed. So when we're looking to build this interval, it's like throwing a fishing net for a stationary fish. If you knew generally where the fish was going to be, okay, and that would be your point estimate, right? And then you threw the net in that direction, that would be a decent example of what we mean by a confidence interval. We are, with knowledge, throwing out that net and saying, okay, because I designed this interval correctly, using the correct method, I can be 95% sure or 99% confident that the true mean does lie in that region, okay, in that interval. Let's figure out how to do that now. Okay, now going back to this list that I made you, okay, we've talked about the point estimate. We're going to talk about the requirements shortly, but now we're going to talk about this critical value. Using the confidence level that we want, how do we find this critical value that's part of developing this confidence interval? That's what we're doing next. Okay, so here's the intro to critical value slide, and this is very important because, as I say, we're going to have critical values every single different type of scenario that we use to find a confidence interval. So here we have this number, z of alpha over 2, okay? Now remember, we've talked about being 95% confident. We've also talked about the confidence level, C, being 1 minus this alpha, which we're going to learn more about as we go along. Okay, so if we, as we saw before when we were looking at this slide, let me go back, there we go, right there. When the alpha was 0.10, then the confidence level was 90%. When the alpha was 0.05, which is 5%, the confidence level is 1 minus that, or 95%, and so forth. So what we're doing here is we're saying, okay, we've got this confidence level. And when we have the confidence level, then we know what the alpha is because it's 1 minus the confidence level. Then we're going to take that alpha and divide it by 2, and it should be the area that's in the tail. Okay, now it's in the area here, and it's the area in the tail to the left also. But what we're looking for is just this right tail. Okay, so it says a critical value is the number on the borderline separating sample statistics that are significantly high or low from those that are not significantly high or low. The number z alpha over 2, okay, which is right here, this is the z-score, which separates the unusual, the significant, from the usual, which is insignificant, all right? So we want the alpha is going to change with the confidence level that we're given in our problem, okay? So if my confidence level was 95, then that would mean my alpha would be 0.05, which would mean my alpha divided by 2 was 0.025. Okay, so then I'm going to look up in the table or in my technology, and I'm going to find the z-score that has a 0.025 in this little interval here, if my confidence level was 95. If my confidence level is 99%,
then that means that my alpha is just 0.01, which means my alpha divided by 2 is 0.005. And so then I would look up the area that gives me 0.005 right here. Okay, and so that's what we're looking for. We're trying to find the z-score that separates this little yellow from the green being the unusual or the significant. Okay, remember they said that that was really a floating number, and we use 2 and -2 when we don't have any other criteria. But here, it's going to change with the level of confidence here. So now, let's look at this one. It says finding a critical value. Find the critical value z of alpha over 2 corresponding to a 95% confidence level. So a 95% confidence level corresponds to an alpha of 0.05. So alpha divided by 2 is 0.025, which is that divided by 2. The figure on the next slide shows that the area in each of the green shaded tails is alpha over 2, or 0.025. We find the z of alpha over 2 is 1.96 by noting that the cumulative area to its left must be 1 minus 0.025, or 0.975. Remember, the 0.025 is to the right, so we'd have 1 minus that is to the left. 0.975 will be to the left, so 0.975 is what we would look up in the standard normal table. Okay, or we could put the 0.975 into our inverse normal to get out 1.96. For a 95% confidence level, the critical value is therefore 1.96. Okay, so let's play with that for just a minute. 95% is, the confidence is going to be 1.96. So here's a picture of it pictorially. Got 95% is our confidence level. Our alpha is 1 minus that, or 0.05. Our alpha over 2 just cuts that in half, and 1 minus 0.025 is going to give us the area that's to the left of this critical value. Okay, so we can look up 0.975 in the standard normal table, or we can look it up using our inverse normal. Let's do that very quickly. Okay, so when I'm looking at my z-score areas in the body of the z-score charts, then I've got 0.9750, and when I move to the left here, I go to 1.9, and then I'm going to go all the way back, and there I have it. I'm going to move all the way up, and I get 0.06. So 1.96 is what I get for the z-score that goes, sorry about that, dropped you. The z-score that goes with 975. 0.975 is 1.96. And every time I do that, I'm going to get 1.96. And it's such a common one. If you look right down to the bottom of your z-score chart, notice what it says. Common critical values. Confidence level 95%, 1.96 is what it gives us in this little common critical values chart. All right, here I just entered the inverse normal here of 0.975, which is the area to the left, comma 0, which is my standard normal mean, and 1, which is my standard normal standard deviation, and I get 1.9599996, which is 1.96. Right, so the next slide gives you the common critical values again. So this was the picture. There's another common critical values chart. And you can see the 95% is 1.96. Okay, so now we're going to work on margin of error. And guess what? This little cheat sheet I made for you. We just talked about critical value, which is going to change with each confidence level. And then we're going to talk about margin of error. And these two go together to give me my confidence interval. So here we have margin of error. When data from a simple random sample are used to estimate a population proportion P, which is what this whole section is about, the difference between the sample portion P and the population portion P is an error. So the first P was a P hat. The second one is the true population proportion, which is P, and we call that our sampling error. Okay, the maximum likely amount of this error is the margin of error, denoted by E. So we want to find our maximum error because we want to make sure that we're very likely to get our true population proportion right in the middle of this confidence interval. There is a probability of 1 minus alpha. Remember, 1 minus alpha is the confidence level C, that the difference between P hat and P is E or less. Okay, the margin of error is also called the maximum error of the estimate and can be found by multiplying the critical value and the estimated standard deviation of sample proportions. All right, so now that's a whole bunch of words, but guess what? Your book's going to give you a formula to do this with.